Right, in this lesson, we're going to look at absolute value equations and absolute value inequalities in one. So here's an example of an absolute value equation. An equation means it has an equal sign, and it's going to also have an expression inside of the absolute value signs. So remember that an absolute value is a positive distance from zero. So for example, if we were looking for the absolute value of 5 minus 8, we would first simplify what's inside the absolute value bars, which is negative 3. But if you think about the number line, negative 3 is right here, and that distance is never measured negatively. The distance is 3 spaces. So the absolute value of negative 3 is a positive 3, a distance of 3. So solutions to absolute values. Absolute value bars can have more than one answer. So for example, if we're looking at the absolute value of x being equal to 7, what could be the values of x that would make the sentence true? So because it's a positive distance, x could actually be a negative 7 or a positive 7, because if we had x set as positive 7, the absolute value, that's a distance of 7 from 0 on the number line. But naturally, negative 7 is also 7 spaces from 0 on the number line. So x would have two possible solutions of 7 and negative 7 in that case. So to solve equations containing absolute value bars, we will start by isolating those absolute value bars, meaning get anything that's not in the absolute value bars to the other side of your equation. Then what you'll do is you will set up two equations. One equation you'll set equal to the positive answer, and the other you'll set equal to the negative of the answer. And we do this because there are going to be a positive and a negative solution that would make this absolute value true. And then we'll solve each equation naturally. And once you do this step here, the bars will go away. Your absolute value bars go away. And I'll show you what that looks like. Then you don't need them anymore. Okay, so here's our first example. Now, step one is to isolate the absolute value bars, which is done for us. So from here, we will set up two equations. One, you just take whatever's in the absolute value bar and write that twice. Keep that part the same in both equations. X minus 7 equals, and one will set equal to the positive answer, and the other we will set equal to the negative of the answer. So I've got one equation as x minus 7 equals 13, and the other is x minus 7 equals negative 13. And this is what I was talking about, where at this step we no longer need our absolute value bars, because by setting one equal to the positive and the other equal to the negative, we are now taking into consideration the two possible values that would make this true. So from here, you'll just solve each separately and get your solutions for x to be 20 and negative 6. So we'll write these in set notation, meaning x is equal to the set of values of 20 and negative 6. And you could try by substituting both back into your original equation, simplifying, and seeing that you'll get positive 13 both times. Here's our second example. This time the bars are not isolated, so we do need to first add 7 to both sides, get that minus 7 to the other side of the equal sign before you set up your two equations. Once you've done this, you can now set your equations up, one equal to positive 22, the other equal to negative 22. Subtract 3 from both sides and solve for x to get x to be either 19 or negative 25. Here's another one. So bars are not isolated. Here we've got 2 times the absolute value of 3x minus 4 minus 1. So to fully isolate the bars, undo any addition or subtraction first. So add 1 to both sides, then divide both sides by that 2 that's being multiplied on the outside. That leaves you with your absolute value of 3x minus 4 equal to 3. Once we've got the bars isolated, we can set up our two equations, one equal to positive 3, the other equal to negative 3. From here, add 4 to both sides, divide both sides by 3. To isolate x's, this is just basic two-step equation work here. and to get x to be equal to 7/3 or 1/3. Okay, there are some special scenarios with absolute value equations. So if your absolute value equals a negative, then the answer will be no solution, or you can also consider this an empty set, because an absolute value is always a positive distance from zero. So for example, let's say we are isolating these absolute value bars here. We subtract 12 from both sides. And at the point at which our absolute value bars get isolated, we are equal to a negative number. This is not possible because the absolute value of anything will always be positive. So at this stage, you can say x is equal to the empty set, or you can say no solution. You can write that out. But this is not physically possible to find a number for x that would make this absolute value simplify to be a negative. So you can only determine this once you get to the isolate of the absolute value bar step. And if at that step you're equal to a negative, then there's no solution. You cannot go further. All right, let's take a look at absolute value inequalities, which you'll see many similarities to absolute value equations. So to solve absolute value inequalities, we do the same thing we did with equations, where we isolate the absolute value bars. This step 2 is a slight difference. You still set up 2 inequalities, get rid of your absolute value bars. One you will set equal to the original inequality in the answer. So one you basically just recopy. The other one you're going to set up to the opposite answer, so the negative, but you're also going to flip your inequality sign. So we'll take a look at that in a moment and solve each separately. Okay, so here's our first example. We've got the absolute value of 2x minus 1 less than or equal to 7. So in this absolute value inequality scenario, we've got our absolute values set or isolated. So step 1 is done. So now we set up our 2 inequalities. One you're really just going to copy. Over here you use the original inequality and number. The other, though, when you set it up, you will copy whatever was inside the absolute value, 2x minus 1, but you're going to flip your sign and set it equal to the negative answer. So this one really over here looks exactly like what we had, just without bars. But over here, notice we flipped the way this inequality symbol was facing, and the 7 became a negative 7. From here, you'll solve each separately, just like we were doing with our equations. So on the left, add 1, divide by 2. On the right, add 1, divide by 2. And we get x to be less than or equal to 4 and x to be greater than or equal to 3. So these are the 2 possible solution sets that might make this inequality true. So with inequalities, we will show that as a graph. The solutions will show as a graph. So we'll plot x is greater than or equal to negative 3 here. We fill it in because it's or equal to. This one goes to the right because we want greater than or equal to. The x less than or equal to 4, we fill in, and that arrow goes to the left. And so I've shaded here the overlap region. So this is an and scenario for this compound inequality that we're ending with, in a sense, because the only solutions that make both of these true land in this overlap region. So to find a solution that will make this original inequality true, we would need a value that falls in here. So to write this, we'll write x is equal to the set of, it's still set notation. And you write your x once in the middle, and then I generally will do least to greatest, negative 3, then 4. It's fine if you had the 4 here and the negative 3 there, though. Just make sure that these symbols are opening to the same thing when you copy them down. So here we were opening to 4, we're opening to 4, we're good. Here we were opening to x, so make sure it's opening to x when you've got the negative 3 and x there. Okay, so here's your next example. I'll let you go ahead and try this one on your own, where you set up your 2 inequalities, one equal to the positive and one equal to the opposite of the answer, and flipping the sign. When you're ready to check the solution, how about pause the video and then click play to check it. Okay, so you've gone through this problem. So here we'll start out with 3 minus 2 are greater than 7, and 3 minus 2 are less than negative 7. Flip the sign and take the negative of the answer. Subtract 3 from both sides to isolate, or to solve for your r. And in this one, hopefully you caught this next step. We divided both sides by a negative 2. And when we divide both sides by a negative 2, your sign direction should flip. So that is just an inequality solving rule we still need to apply even in absolute value inequalities. When you multiply or divide both sides by negative, your sign flips. From here, graph your solutions, and you will see that this is an OR scenario because there is no overlap. So, oh, I must have accidentally moved this down, but anyways, r is less than negative 2, looks like this. R is greater than 5 is an open circle pointing to the right. So this is an OR scenario. It would have to make one or the other true to make this inequality true. There's no overlap, so it's not an and. So you can write your answer like this, or you can write it with one R in the middle, negative 2, 5, and it's opening to negative 2. It's opening to R. So this is another correct way to write this solution set. Okay. And here's our next example. I want you to notice in this one that we're starting out with an absolute value, and it is isolated, and we've got a negative number over here. So just like with absolute value equations, if you've got your bars isolated and set equal to a negative, that should raise a red flag to you that something a little different's going on here. We know that an absolute value is always a positive value. So here we've got a positive, whatever 2y minus 1 is, when we take the absolute value of it, it will be positive. And we're saying this positive should be greater than or equal to negative 4. Well, you could certainly solve this. However, any positive is always greater than a negative. So since all absolute value answers are positive, which is always greater than a negative, this statement is actually always true, meaning that your solution is set equal to the set of the real numbers. This is all real solutions because any number will make this inequality true. And naturally, the opposite of this occurs if you've got an absolute value set less than or equal to a negative. Here we've got a positive. We know an absolute value is always positive. Set less than or equal to a negative. Well, a positive is never less than a negative. So this is an example of a false statement, meaning no solution. There's no solution for y that would ever make this inequality true. So when you've got your absolute value bars isolated, set equal to negatives or less than or equal to negatives or greater than or equal to negatives, that should be a red flag, and you need to figure out, is this an all real situation or a no solution situation? And there's one last practice problem for you to try. I'll let you do this one on your own. Pause the video. When you're ready to check, click play. Okay, so you should get, for this problem, an OR statement of y needs to be less than negative 2 or y needs to be greater than 4. If you did combine those all in one, you would have the y in the middle, negative 2, it's opening towards the negative 2, 4 would also work. That's another way you could write your solution. And we are all done with our absolute values lesson.